Good morning, Hugh.
Good morning, Jason. How you doing?
Very well. Happy holidays.
Happy holidays to you as well. You and the team and the family.
We are doing very well and very excited to have this long-awaited interview with you today.
Yes. Yeah. Thanks for making the time.
And we'll jump into it. You successfully built and exited a B2B SaaS company. What specifically did that experience teach you about capital efficiency and sequencing that applies directly to a capital-intensive aerospace business?
It's a great question, and
Thank you.
we get that very, very frequently because obviously building software is naturally capital efficient relative to building rockets. That ultimately is probably about a $500 million journey. But I think the biggest kind of crossover and learning is centered around the team. I think a lot of people say, attracting A players and building an A team, and in some ways it's often overused. And the definition of A players also is really kind of hard to come by until you actually experience it. And that was something where after we had done our seed round at my last company, it kind of hit us that, we were bootstrapped for 4 or 5 years, talk about capital efficiency. And you're really trying to go contract to contract and revenue to revenue. And that creates almost like a Frankenstein product because you're being forced to go where the money is, not necessarily where the long-term opportunity is. And you try your best to bring that together, but often you end up with a Frankenstein. So, and because of that as well, you also can't attract necessarily like the top talent because you don't have the capital that's needed to do that. So we were kind of hyper-focused post-seed round and kind of turning over and optimizing our team. And, super proud of how that kind of panned out after about a 1.5 to 2 year journey. We essentially turned over most of our executive team. A lot of our developers, we worked with focusing on experience and senior talent versus a more junior to intermediate. Because you also need the senior talent to kind of help guide the junior team as you bring them in. And we just didn't have the senior team to guide our existing junior team. So we did a little bit of a switch over there. Team ultimately is the key driver and factor. And it kind of dovetails into what I like to call the Canada problem. And it's that as Canadians, we're very complementary regardless of what the reality is. And I think Canada does not have the talent in the country. I'm going to sound very like anti-Canadian, non-nationalistic, but just being realistic. And I think it's really important, especially as you're building a capital-intensive business, the talent doesn't exist in Canada. And that's a big component of driving for capital efficiency in a capital-intensive business. Because if you look at Europe, the UK, Australia, those countries have taken about a decade to get a small lift rocket, so call it 500 kilograms payload to orbit into, actually they haven't gotten it yet. A couple have attempted to get off the pad, been failures, which is normal, but 10 years and $500 million, give or take, which pales in comparison to the US. If you compare it to like a Firefly, Rocket Lab, SpaceX, they're in the $100 to $200 million range, and call it the 4 to 6 year time frame for small lift. And a lot of that is just based on the US has a ton of talent that has worked within the realm of rockets, whereas globally, that's a very rare talent. So that's where we're focused on bringing as much of that experience, both from the US, Europe, UK, Australia. They've got learnings because they're 10 years ahead of us. So we can leverage their expertise and understandings. And I think that's ultimately our competitive edge, both within the Canadian ecosystem, but also in the global ecosystem. So that's been a really core focus. And that's where part of building out our founding team. So David Tenney was at SpaceX for about a decade. He was working on the Falcon 9 reusability campaign. So he was part of all the testing, manufacturing, all the way from essentially test through to watching and being part of the launch at the Cape. And he was there during the mid to early 2010s, which is kind of like OG SpaceX crew, which comes with a ton of different kind of learnings and experiences that you otherwise wouldn't get today, because SpaceX is now, 10, 20,000 folks. It might actually be a lot larger than that. So as you're coming into the company, you're seconded to like a very small portion of the rocket or component, and you don't have that like full-fledged and full lens understanding. So hyper-focused on the team component. And then also, I think the team goes beyond just like the current team. We also have a stream of advisors, one of which is Mina Mitri, who's the CEO of Kepler. It's essentially the second largest commercial constellation provider in Canada and growing. So he's been really helpful in the early days. And the commercial aspect is vital to our long-term opportunity. We also have David Sinclair, or Doug Sinclair from Rocket Lab. He sold his business. You and I both know him through CDL. And then a couple really exciting folks that I can't formally announce quite yet, but some of which are connected with the Canadian government, as that's an important part of our story. And that's really kind of been my focal area to kind of build the best foundation possible to kind of give us that long-term capability and ability to be as capital efficient as possible, to learn from the mistakes of others and kind of push through from that perspective. I feel like I probably answered like 20 questions in one there.
No, that's perfect. It does segue into how do you personally think about your role over the next 36 months? The builder, capital allocator, recruiter, government integrator. How does that role evolve over time?
Yeah, I'll probably, triple down on team building. That's going to be the most important component over the next 12 months. We also have a SpaceX avionics engineer who was on Crew Dragon. He was there for about 7 years. Also Canadian, which is a great part of the story, bringing Canadians back home. So we've got him joining the team, and we've got another probably 6 or 7 roles that we're hyper-focused on in and around propulsion, turbo machinery, structures, GNC, aerodynamics. Like there's a lot we have to hire for, but the team should, end up being, 10 to 15 core engineers over the next, 12 to 24 months as we kind of build that out. So that's core area number 1. Core area number 2 is government relations. So we've hired a GR firm, Anstone Group. They've been really helpful. I was in Ottawa right before the holidays, more than I ever thought I would be in Ottawa for my life. And it seems like it's definitely a trend. GR, government relations, is a key part to this journey, because to make the investment case close from a VC perspective, you need both capital efficiency as well as non-dilutive funding, because otherwise it's just not large enough of a multiplier on exit to make that really work. The good news is that the Canadian government already has a $105 or $110 million RFP that's out for light lift, and then they'll have another 20 to 30 million in the middle of next year for medium lift, and then there's another tranche for talent development, which we believe we're kind of able to participate for all 3 through partnerships and the existing ecosystem. So that's kind of, tranche 2, which is really government relations, and that blends into tranche 3, which is capital. There's no way of getting around it, but we need as much capital as possible. And that's where, starting with this round as a strong foundation, we've got essentially all of the tier 1 venture funds in Canada, Ripple Ventures. We've got the BDC, which is also great as a signaling, both from the government of Canada, but also within the GR meetings, for them to know that essentially by them. It also really helps from that perspective. Ripple Ventures, Panache. And then we've got some really exciting angels like Toby from Shopify, Mike Katchen. There's David Hariri from Ada, Matt Lozak from Allo, building modular nuclear reactors. So we're really trying to build out a, call it capital base that can help us with that next raise as well, and kind of build that momentum. Because 2 things kill rocket companies. One is lack of capital. The other is trying too novel of an approach to an already complicated engineering problem. And both of those are areas that we're hyper-focused on. I'd love to say that I'd be like the physical builder and the engineer, but though I did take mechanical engineering, I'm not a rocket scientist, and I know where I'm best kind of able to focus for the business and growth.
Why is a propulsion-first strategy, specifically reusable ethalox, the correct wedge for Canada's sovereign launch ambitions?
Yeah, I like to think of this as kind of like a broader problem to sovereignty. Sovereignty is what enables the opportunity to build rockets in Canada, but it's not a long-term, I think, economic opportunity. And the main driver there is that the world shifts between sovereignty and isolationism all the way to globalization. And why are we all working on the same thing? Like, wouldn't it be more efficient if, we share resources, which is where we were pre-Trump and trade war. And I think ultimately we need to be prepared as both a business and a country for when that world shifts back to globalization and the world says, hey, why does everyone need a launcher when we could just share a couple of them? And I think that's ultimately where we're hyper-focused, is we need to be economically competitive on a global scale, not just a Canadian scale, because the Canadian industry also doesn't exist today. And when the world shifts to globalization, that's going to be our largest opportunity, is to win on economics. So the best way to do that is to leverage the bleeding edge technology that exists today. And Methalox is a clear kind of winner for a reusability component. It's kind of like in between hydrogen and kerosene in terms of, call it like efficiency, it's and cleanliness. Hydrogen is just really difficult to work with. And kerosene, you can't actually access RP1 or some of the refined rocket fuel products that are ITAR bound, which restricts the ability to bring that into the country. And RP1 was really developed to be a cleaner burning fuel relative to, call it like jet fuel, et cetera. So you'd have to put in a lot of NRE or non-recurring engineering into validating whether you're using jet fuel or whatever derivative of kerosene into your engine, both in terms of making sure it's like burning efficiently, because if you're going to use like an RP style cookbook or derivative engine, but you're not using RP1, there's going to be drawbacks. So you've got to put research and development into that, and then also potentially refining your own fuel source versus just putting that NRE or non-recurring engineering into Methalox, which is a slightly more difficult problem to be solved, but it's also not impossible. And it's also been done before, both in Europe with the Prometheus engine. You've got China, and then of course, SpaceX, Blue Origin, and a couple folks in the US. So it's not unobtainium. It's very much bleeding edge. And I like to equate building rockets to building cars, not in terms of the engineering challenge, but more when you build a car, it doesn't come to market until, call it 7 years after you put pen to paper. And rockets are similar. So you have to build for the future environment, not the current environment. And that's where we've been kind of hyper-focused on making sure that we're cost competitive. And that's really the main driver for us and our kind of technical choices.
I'm just going to re-record the question too. Why is a propulsion-first strategy, specifically reusable Methalox, the current... Oh, geez. Do it again. One sec. Why is a propulsion-first strategy, specifically reusable Methalox, the correct wedge for Canada's sovereign launch ambitions? Okay, perfect. Where do you draw the line between engine maturity and committing to full vehicle integration, and what signals tell you this over time?
Yeah, that's a great question. I think it really comes down to speed, and it really comes down to the pace, largest potential customer, which is the government. So non-dilutive funding is a very important part of the business. It's not what makes the business, but it's what makes the returns viable from a private investment perspective in an otherwise small space economy that is Canada. Obviously growing, lots of opportunities, but that's a key part of it. You can actually run out of money by moving too quickly or past what your existing partner can provide. And I think that's ultimately where we're going to have to do a lot of balancing. So our understanding is that medium lift will be a 10-year expectation within the government. 10-year expectation makes a lot of sense. It's based off of what they've seen other countries attempt, and they're defining it as 4,000 kilograms to orbit. We're defining it as about 6,500 kilograms to orbit, just because satellites are getting heavier, not lighter. And again, it's important to kind of future cast in terms of the types of constellations that we would be kind of participating in helping launch. I think that's really kind of our limiter, because I do believe the capital's there. There's a lot of focus on a dual use. I do feel like there's a huge opportunity to bring in all the talent that we'll need. A lot of people want to work on a clean sheet rocket design, and a lot of people want to move to Canada. It's a great place, though right now it's very cold, but that's temporary for at least a couple months of the year. Be able to move really, really quickly, and once you have that talent density, our expectations are being able to develop and launch a rocket that's competitive with what you would see in the US rather than, Europe, UK, Australia, and others, because we're attracting and bringing in that talent. I think ultimately our kind of litmus test will be I think a pre-engine full-scale hot fire. We'd start the development of the other components. There are elements that are linked to the engine, such as call it like avionics. Yeah, you need like the flight computers, and ideally you're using like the same flight hardware that you're using on the test stand. I think the flight termination system will be something that we're going to look to potentially co-develop within the Canadian ecosystem and do that potentially with actually other, call it competitors or other rocket companies. Because I think there's not enough talent to capital for 3 companies. So let's try to, do our best to work together on non-critical components. But in terms of, full scale development, our expectation now is essentially, 18 to 24 months, we should have a hot fire. And that'll kind of be our litmus test for, okay, now we're ready for the rest of the vehicle, save for some of the components that are required or have like a longer development time frame. That's kind of how we look at it. But again, it's really going to depend on the pace of the government, because if they're going to have smaller non-dilutive financings for the first 5 years, then it probably doesn't make sense for us to substantially scale up until we're either meeting where the government wants to be or pulling the government forward and saying, hey, we've got this capability. Let's start kind of really working more formally together. So that'll also be kind of part of, one of the questions on, the time I'll be spending. And a lot of that will be on GR, educating them on our approach, our capabilities, and trying to find that perfect balance between both vehicle development as well as, our largest potential customers' needs from that perspective.
What design decisions are making today that implicitly optimize for reuse cadence rather than just achieving first fire or first flight?
Yeah, it's actually a very interesting, there's 2 approaches. You've got like the Stoke space, which they've gone full reusability right out of the gate, which is fantastic. They've raised $1 billion. I don't know if that amount of capital is available in Canada, nor do people believe that the Canadian market is large enough to warrant that amount of capital upfront to build and develop. So I think that's one path where you bake it in right away. The other path is the SpaceX approach, which is you kind of iteratively, let's first focus on bringing it up and into space, and then let's iterate on our reusability campaigns. And we're probably going to do more of the SpaceX style approach than we will on the Stoke side, with the caveat that, Methalox is a good example of a choice to, okay, like that's higher reusability, slightly better efficiency. So let's, focus there. I think we're also looking at stainless steel as the airframe. That has pros and cons. Pros being it's, as you've seen with Starship, but with the con being that, the smaller you are, the more parasitic mass you have. It has like an outsized impact to the overall vehicle. So I think that's a trade that we're going through today to try to figure out, in an ideal path as well, you could use like stainless steel fuel tanks. Super heavy, but easier to manufacture. And we don't have a lot of the supply chain and manufacturing capabilities that they do in the US. So it's, we also have to kind of design for manufacturability, but also for manufacturability that's possible within the Canadian ecosystem. Again, depending on the speed of development that we need to go. So I think that's really kind of how we look at it. But I'd say we're more iterative, because just getting a rocket off the stand is a very difficult and challenging engineering and manufacturing problem. And I think to try to overcomplicate it with an even harder problem of bringing a rocket back and landing it on a platform, which only 2 companies have done to date in the world, I think we'd be biting off too much. But there are little nuances, again, like the propulsion system, and there are some areas that we could leverage early on. And that's where, David's experience will come in on like the sub systems potentially as well. But that's kind of how we look at it and view it. It's really about trying to be as capital efficient as possible to get to orbit, prove the capability, and also prove the reliability. So I'd prioritize reliability over reuse, at least in the early stages, because if you're not 99.9% reliable, no one's going to fly on your rocket, no matter how cheap it is. And Astra showed us that story, and that's ultimately where we're hyper focused on, and then we'll bake in reusability over time, with the caveat that if there are easy wins, so again, Methalox, put it in quotes, as easy, nothing's technically easy, maybe stainless steel airframe. There are lots of different areas that we can kind of look to trade, as long as it doesn't impact potential reliability or it's substantially higher on the non-recurring engineering side of things, is how we'd approach that problem.
To re-record the question as well. What design decisions are you making today that explicitly optimize for reuse cadence rather than just achieving first fire or first flight? How conservative are your assumptions around engine life and turn count at this stage, and why did you choose those assumptions?
Yeah, we've kept it actually pretty low to about 8 to 10 reuses, which SpaceX, I think, and you can correct me here, it was like they've done their 50th on one of their boosters. Might actually be substantially higher than that. But the main reason there is conservatism, baking that into the model. The other component is, again, SpaceX is the only company who's successfully fully reused a booster multiple times, at least to date. So I think when you're modeling these things, I've seen a lot of and heard of a lot of rocket companies who model, extreme volume after like the first year of getting to orbit. It's like, we're going to get to orbit in 4 years. And then by year 5, we're going to be launching, 10 times. And that's just historically never happened. Usually there's like a year lag between the first and the second launch. And then it takes another year or two before you start getting into enough of a cadence. So I think that's one component. This is an extremely long time horizon problem to be solved. And B, I think it's also important to figure out, and I don't want to call it like the worst case scenario, but ultimately our goal is to get international payloads into space, because the Canadian ecosystem and market is not huge. And if you don't have a massive end market, and reusability starts to kind of not make sense. And Europe's actually a really good example of this with Ariane 6, Ariane 5, Ariane 6, in the sense that they felt like they didn't have enough volume in the European market to warrant reusability. So they did a fully expendable rocket, to their detriment, because the market ended up growing way past, and now they're talking about building a heavy lift launcher in Europe as well, which is also super interesting. So we're building for that growth within the Canadian ecosystem. It's coming. There's been probably $1 billion in announcements over the last couple months. Actually, much larger if you include the kind of already announced military constellation. So it's like $6 or $7 billion in investments over the next 5 to 10 years, which is significant. And there's going to be a lot more commercial players within that ecosystem too. So not worried about the end market from that perspective, but more focused on how do you make the economics work, and what's that bare minimum number to get you in and around that, call it $1,000 per kilogram mark, gets us there. So anything on top of that is absolute gravy. And I think that's an important element to also point out from an investment perspective, from a government perspective, from a customer perspective, is are we assuming unobtainium results to get the economics to work? And essentially the answer is no.
What technical or organizational factors would cause you to delay moving from subscale to full-scale engine development, even if capital were available?
That's a great question. And we've spoken about this a little. I think it, ultimately if capital was available and it wasn't a limiting factor, you would almost probably skip subscale and you would just go full scale. Subscale, and our limiting factor there is essentially the pressure from the tanks. And we want to have essentially the same ratio of flows going through the engine. And our limiting factor there will be the pressure coming out of the two tanks, one for the liquefied natural gas or methane, and the other being the oxidizer or liquid oxygen. I think ultimately, and maybe we'll have to re-record this question because I kind of have to think through it, because ultimately there's no capital is essentially the decider of how quickly you move. So I don't really know if we wouldn't essentially move forward on a specific milestone, because we'd essentially say, okay, we've got learnings, now we're just going to use those learnings and scale it up, is probably the path. But also David would probably have the better perspective on that, which we've spoken about. But that's, we're essentially using the subscale as a proof of concept to raise the capital. It's almost like used as a gateway for that next tranche rather than being a full technical breakdown, because as you scale the engine, you get more interesting, call it, problems to be solved that may or may not appear on the subscale side of things, if that makes sense. So maybe we'll try that one
I've
one more
highlighted
time.
that in the question set. So
Okay.
we can leave it for now. What does a successful subscale hot fire in Q1 2027 mean in concrete, measurable technical terms?
Yeah, essentially, depending on the pressure that we're designing from, and that pressure will be dictated by essentially the pressure of the tanks and the outflow. The engineering, call it design, is designed to be at a similar ratio as what you'd have on the full scale with a turbo pump. So on the subscale size, it's pressure fed, which means it's just being fed directly from the tanks. There's no turbo machinery in and around that to essentially increase the pressure as it goes through the engine. So a successful hot scale would be, fired for a few seconds. You see literal fire coming out of the engine, hear it, feel it, see it, can't touch it. And that'll be from a kind of physical and observable result. And then from a technical perspective, it's making sure that all of the components as well were able to sustain that temperature, et cetera, within the engine.
In Methalox engine development, where do programs most often fail? Ignition, cooling, materials, or operations? And which of those risks concerns you the most?
It's a good question. I think operational, it is more difficult because you're working with liquefied natural gas. So it's cryogenic. You have to keep it cool. Otherwise, it boils off. So that's probably one of the larger areas. Kerosene, you can just keep it in a tank and it's stable at room temperature. That problem is solvable because LNG is transported, and liquefied natural gas is transported throughout the world. We actually have that expertise in country, which is also fantastic within the oil and gas sector in Alberta and to some extent BC, where they're shipping the LNG. Definitely, all of these are solvable problems. It's been done before. But if you put it in relation to, call it like a traditional kerosene engine, that is one area of difficulty. The other is it does burn hotter. So there are certain trades you have to do within the subcomponents where you would see engine failures where you wouldn't from a kerosene perspective. Methalox also isn't as well studied, call it, in the open. So in the US, they have databases of certain alloys and materials that burn under certain temperatures and pressures and react through different fuel types. But we can't access that in Canada because A, we don't have that data in Canada, and B, it's covered under ITAR. So it restricts the ability for that information to leave the US. So we'd have to do a decent amount of experimentation on certain alloys to ensure that you're also trying to figure out the thrust to weight. You could solve all these problems probably just by having significantly more dense, call it, materials. But then the trade-off is it's now a very heavy, overcomplicated engine, and it offsets any of the potential or perceived benefits of that fuel type. That's kind of like the trades as we go through it. It's obviously been done before. We just have to kind of start again from first principles and build through that, because the data sets and knowledge that does exist is mostly inaccessible to us. So I'd say that's probably the other kind of more challenging part of building out a Methalox engine.
How much of your test philosophy is informed by Falcon 9 reuse learnings? And where do you believe CRC must deliberately diverge from that model?
Yeah, it's a good question. Falcon 9 has done a great job on the reusability. of like a kerosene engine. So, they have the coking problem or soot or essentially like the nasty black stuff that builds up in and around the engine. But they've been able to essentially reuse the booster a substantial number of times, even within that situation. They've also, I think, learned into the Starship era where, no part is the best part. So, removing landing legs and using chopsticks, I think is an interesting approach. Makes a lot of sense. I think, they also did full stainless steel. They did full two-stage reusability. Stoke Space, very similar. I think they're gearing more towards the Starship style rather than Falcon 9. And then, of course, Methalox, I think, in theory, helps with the reusability because there's less that has to happen. One area that we've been speaking about is, making sure that we have a really strong digital twin and also trying to, maybe there's opportunities within AI that didn't exist when Falcon 9 was being developed for like non-destructive investigation of the full system. In the best world, it's just like an airplane. The airplane lands, there's sensors, etc. And also the way that it's being engineered, that it should have like a certain number of hours before it has to get serviced, etc. Rockets should be the same. And that's ultimately what we should be gearing for. And I think with the advent of, AI and other technology tools that didn't exist during, the Falcon 9 reusability campaign, I think we could definitely take a much better approach, let's say, because they're essentially sunsetting Falcon 9 and just putting it all into Starship and to call it like the newer technology types and focus. And that's also kind of where our focus is as well.
What does your test stand architecture allow you to learn faster or more safely compared to peers at a similar stage?
And when you say peers, would that be Canadian peers, global peers?
It'd be global peers.
Yeah, I think, from a test stand perspective, I'd say the best thing you can do is have it as close to the factory as possible. If, speed is the name of the game, and ultimately you're doing, call it 2 tests a day, you need to be able to bring certain parts or derivatives of certain parts quickly to the test facility. And the easiest way of doing that and quickest way is to be within driving distance. So we've got like a 3-hour driving radius of where we're trying to figure out to put both our factory and test facility, as well as machine shops, whether it's locally or again within driving distance, that we leverage internally. That's probably the biggest driver that you could leverage within call it like the test, fail, iterate loop cycle. We're also building our test facility essentially like a trident. So we've got our subscale tests, our full scale, and then potentially horizontal, but that also hinges on, a lot of this is going to be the first in Canada because ours will be the largest engine developed within the country. The other 2 Canadian peers are more focused on smaller engines and clustering for both the small and medium lift. Harder for that to scale into medium because now you've got a ton more plumbing and architecture, whereas we're kind of taking the Falcon 1 to a Falcon 5 approach where we'll have one engine for our light lift, kind of more like test vehicle, and then 5 to 7 engines clustered for our medium lift or 6,500 kilogram payload to orbit engine. So because of that, it also comes with stringent, call it test facility requirements, which we're currently working with a couple counties, cities, airports in Northern Ontario and I guess South Northern Ontario. That's driving distance to where we think we'll probably have our integration and manufacturing facility in the GTA. So we'll have that 3-hour driving radius and ability to kind of test and iterate as quickly as possible, as well as making sure that we can essentially do 24/7 testing. The other, I think, key driver is you got to test often. So a lot of this isn't in the engineering or the architecture, but it's really in the site selection. And I think a lot of people are either hamstrung by zoning or, the local town nearby and a lot of restrictions that come in around that, maybe during fire season, if you can't test for 6 months, that's detrimental for your development schedule. So we're really kind of hyper focused on making sure that the site that we do select has all of those keys so that we can essentially test as often and frequently as possible.
If early hot fire testing reveals a major issue, what is your pre-planned response path rather than your optimistic recovery scenario?
And when you say issue, is that more just kind of an engineering failure or?
Yeah, it could be an engineering failure. It could be just very simple, like something isn't working, um, and we just simply don't know what it is.
Yeah, I imagine that's going to happen very frequently in a lot of our different components. So I'd love to say that it's going to be a very smooth process. Everything will be on time, under budget. Ultimately, I'd say it comes back to experience and bringing as many experienced heads into the conversation as possible to make sure that A, we're learning from previous mistakes that were learned historically. So that's one component. And then B, when we're having troubles, part of it's also just, are we taking the right engineering and scientific approach and asking the right questions? And I think if we've got folks that are able to ask the right questions, as well as if we have access to folks that we can ask those questions to and continue to develop that in-house, it's going to be a very iterative approach, test, fail, iterate loop. And that's ultimately our expectations of what will happen. We expect failure because that also means that you're testing on the bleeding edge of what's possible and what's not. In the situation, as you mentioned, where it's, hey, we don't have an answer to that, path one is rapid experimentation. And it's, try to challenge your assumptions and just change different parts. So that's where, again, being really close between the factory and the test facility is really important so that you can rapidly kind of make breakthroughs through those kind of stalls. And the other is that rocket scientists are surprisingly easy to get a hold of and experts. And a lot of people want to help get humanity off this rock, which is like the common kind of quote. So I also think there's an opportunity to continue to have that naive ambition and to also throw our egos aside and realize that we may or may not be the smartest within a very specific subsystem or component that we're developing. And if there's bound to have been someone in the world that solved that problem before. So it's just, reaching out to as many people as possible to help kind of iterate through that path. Because, for the first 2 years, call it, we'll be a team of 15 and very, senior and seasoned engineering experts and people with experience. But it's still just 15 people. And there's thousands of components that have to be built and developed. So ultimately, if we can leverage, advisors, consultants, and I think that's the right path to take, and to not be stubborn and say, we can do it all ourselves because we're the experts in this space. We are experts, but I think being able to leverage the ecosystem in that way will be a huge help with that.
Since sovereign launch was formally elevated in the Canadian federal budget, what tangible behaviors or commitments have you seen change inside the government?
So all of this is with the caveat that my interactions with the government up until, call it 6 months ago, were submitting tax returns and maybe, having questions on why they're taking so much money. But ultimately, through both the government relations firm, as well as just speaking with folks both on the ministry side, as well as on the administrative side, there's a huge, I was shocked because I was expecting to kind of just be politely, let's just say, like, smiled through the conversation. Like, that's like such a great idea. We don't really have much funding here, or, not really sure how we can help. The conversations were in the literal opposite direction of that, where it was like, we have been instructed by the Prime Minister to move quickly and to get this done. So what can we do to help? And initially, our first goal of these conversations was just to build awareness, to say, hey, we exist, we're building this thing, we've got all these experts from around the world joining the team. It's a great story for Canada, and it's also the right way to approach a very technically challenging problem. What ended up happening within about 10 minutes of those conversations was they jumped straight to, how can we help? What do you need? How do we accelerate this? And that surprised both myself and the government relations firm. So there's a huge fire under everyone within Ottawa to move quickly to dispense of capital as quickly as possible, because they also have to get to that 5% NATO target, which, it's hard to spend money. And especially from a government perspective, it's really hard to spend money effectively and efficiently, because ultimately that's, yours and my dollars going in. And we're always looking and making sure that it's going to the right places. So that's a huge shift that's happened since Prime Minister Carney came in, to the point also where we were sitting in with the Department of National Defense. And the first thing that came out of the conversation was, we have the money. Just tell us what you need and where you need it, and we'll get it to you. And the other actually marked change is the appetite for risk. And ultimately the government, and this is all in the context of government, they're obviously not going to be crazy risk takers, because I think by definition, a government cannot be that in most situations. But traditionally for non-dilutive funding and grants, they also need to see the business living for at least 3 years, have, a certain number of employees and revenue streams. But I think they also understand that, especially within the startup ecosystem, and to help deliver innovation and that kind of line of thinking, they realize they also have to pull back on some of their more stringent restrictions. And that's also something that we've been told there will be announcements in the next few weeks in and around the industrial policy that's coming out of ISET as well. Between that, the conversations of everyone saying, how can we help? The follow-ups after the meetings as well were also fantastic. There is a lot of drive in Ottawa to get this done. And sovereign launch is outlined as a core area within the budget. And it comes all the way down from the Prime Minister's office as well. So there's a lot of focus on this, and a huge opportunity for us in the ecosystem to deliver what the government wants.
Which specific Canadian missions or programs are most likely to become credible anchor demand in 2030 to 2035 timeframe?
Yeah, it's a great question. You can kind of split it up between both military as well as commercial. So we've been chatting with Telesat. They're publicly traded company, and their core focus is really around economics as well as scheduling. And their constellation will be starting refurbishment in the 2034, 2035 timeframe. So, working early with them to find and optimize our vehicle for their constellation type, so that we can, hopefully meet their requirements on economics and scheduling. Reliability, of course, is paramount for anyone. So Telesat would be the largest anchor customer, as would Kepler. And we're obviously working very closely with Amina at Kepler. He's very invested in ensuring that Canada also has a sovereign launch platform. So making sure that we work with him and his team as well to ensure that we've got, again, economics, reliability, scheduling. You'll pretty much hear those three things from every commercial customer. It wouldn't be a surprise. And that's where, sizing the vehicle correctly is important. And those are changes you can't really make post-development. So that's where we're starting right now, working with everyone for that next kind of 10-year journey. On the military side, there's 2 programs that have been formally announced. One is a 3 constellation, like a RadarSat Plus, essentially constellation. And then there's another one, which the acronym escapes me. It's 5 or 6 letters. And that's also an Arctic surveillance platform that should be post 2035 or 2036. They might try to bring that back. I imagine they're going to bring that back. And then I've also heard rumblings that they will be transitioning from the existing 2 to 3 constellation to, hundreds of satellites, especially in the space control domain, which a lot of global governments are focusing in on as we militarize space. So I expect there to be substantial demand from the Department of National Defense in the 2035 plus timeframe, as they are also working through their strategy there. There will also likely be maybe a Canadian Space Agency Pathfinder mission. So maybe they'll provide either free or discounted launch to Canadian companies on a Canadian sovereign launch provider. All of that to say there's probably about 8 or so launches per year of domestic demand. And then our goal is to then use that as a launching pad for our broader business internationally. So once we prove out, because there aren't a lot of medium lift providers globally, there's this bifurcation between light lift, which has mostly been proven that it's just uneconomical and people would rather just mostly go on rideshare. And satellites are also getting larger. So light lift was a thing in the 20s, and it's slowly kind of going away as the world transitions. And then you've got heavy lift on the other side, because that's where there's substantial demand from the NASAs, the ESAs of the world for exploration, for lunar and Mars missions. And there's this missing middle, which is more geared towards low Earth orbit constellations, as well as sovereign mission types. And that's where the Falcon 9 utilization of dedicated commercial and sovereign launches is like 3,500 kilograms to LEO. So most rockets are being underutilized today, but they have to be the size that they are to participate in these massive billion-dollar plus government contracts, especially as like new space stations are coming online and there's a lot of infrastructure we're sending to space. So those are essentially like the trucks. And then we're kind of like the Ubers or whatever equivalent in the transportation realm. And that's where I also think sizing the rocket correctly really helps with the economics. And that's where we can also have a huge opportunity to bring in international demand as well. And then as the world shifts to globalization, there'll be other cannibalization of other global rocket companies. And then you're building a very strong case for Canada to be a core participant in the global launch ecosystem and economy, which is also very exciting.
You've already touched on the following question, but I'd like to expand on it further. How do you leverage government anchor customers without becoming structurally dependent on a single buyer initially?
Yeah, I mean, that's critical because if you rely on one single customer, which is the government, because of their cost structures as well, you're probably not going to become economically competitive in a commercial sense, unless you're subsidized. And then you're exposed to the whims of whichever government is in power at the time. And that's what kills companies. So I think making sure we're engineering both the business and the product to not be solely reliant on, especially government contracts. Because I also don't think that that's what the government wants, is another company that they have to sustain into perpetuity. So that's where, again, focusing on building relationships and understanding the requirements that are needed on the commercial side of things, and not just, one commercial player. It's as many commercial players as possible. And then on the government side, it's making sure that we're kind of blending the two together. I don't think, as long as the vehicle is sized correctly, both in terms of diameter as well as payload to orbit, you aren't necessarily pigeonholed. Government will just require a lot more overhead for like security, because a lot of their payloads will probably be classified. So there'll be a lot of operational overhead that'll be required. And that operational overhead will cause likely your commercial economics to also increase, because now you've got more overhead overall that you have to service. Unless the government, which we've seen historically, the government will pay more for their mission types because it requires that, in which case it's not having as much of an impact on the commercial side of things. So I'd say that's really just kind of designing for multiple folks in mind. And that essentially starts today, because as soon as you start manufacturing and as soon as you've, cemented the technical plans, I don't want to say there's no turning back, but it's really hard to shift a rocket design once it's past a certain point.
Why will CRC succeed where prior launch efforts such as Virgin Orbit or Astra ultimately failed?
Yeah, I mean, it's interesting you use those two, because they also fall under the category of novel manufacturing or engineering. So the two things that kill rockets: novel engineering and approaches, the other being a lack of capital. And I think Virgin Orbit tried to launch rockets from planes, which is an interesting, novel approach. But when there are so many things trying to kill you as a business, especially a rocket business, and you're trying to take a novel approach that's almost kind of unnecessary, you're putting a lot of undue risk on an already very risky venture. And Astra also did the same, where they thought, okay, like instead of reuse, we're going to go heavy into manufacturing and mass manufacturing. And if we build enough rockets, the cost comes down and we can just, launch one a day. But I think, unfortunately, and I believe these are the words from Chris Kemp, which is reliability is the product. And I don't think they thought through that in the early design lifecycle. And that's also ultimately where they failed. So Relativity tried to 3D print everything, and it just doesn't make sense. 3D printing is more a tool rather than a product. And I think they productized 3D printing. And a lot of that was just driven through, how do you get as much investor capital as possible? Through other words, AI, 3D printing, and as many different things into the pitch deck and approach, and keep pushing that through. On the flip side, it's great that these attempts were made because they're attempts to push the industry further in novel ways. But historically, I don't think there's been a single company that has pushed a novel rocket that has worked. And I think that's really, really key. And that's, in the words of David, my co-founder, it's how do we make launch simple and boring to the point where it's like, okay, like another one's launched. It's like, all right, on to the next one. And I think that's ultimately the key. And it sounds really unsexy, but it's the reality. And I think it's also the seriousness that has to be taken towards a very technically challenging approach. And that's our...
What does CRC do meaningfully better than Nordspace and Reaction Dynamics? And what do those companies do better than CRC today?
Yeah, it's a great question. So Reaction Dynamics is hybrid propulsion. I think Bashar and his team have done a fantastic job in pushing the industry, the Canadian industry, to where it is today. I think that the only limitation there is that hybrid propulsion is, they're solving a 90-year-old engineering problem, which could fall into that novel engineering path that we've spoken about a few times. And it also doesn't scale well past light lift. So assuming the technology does work, great for light lift, but it doesn't really scale through like a thrust to weight going much larger. So ultimately, I think they'll be left with the choice of, do we go into liquid propulsion? And if that is the case, you've got to bring in different expertise and experience, and you're essentially rebuilding from the ground up with not a ton of heritage to work from that perspective. Nordspace is kind of akin to the first question you asked, where they've been bootstrapped, and for everything that they broadcasted, they'll continue to be bootstrapped, which is very difficult to do within the launch business. And because of that, they're hyper-focused on a lot of different product lines, which I think is detrimental to any business, let alone launch. So I think that's a core component that I think launch needs a full focus and full attention. And then just kind of across the board, we're really focused on bringing in as much talent and experience as possible. And both of those companies have been home-growing talent, which is great. But that also means that you're going to be making a lot of mistakes that you otherwise wouldn't have made if you've got experienced folks who have seen it and done it before. So that's really kind of our differentiator from that perspective.
How critical is ITAR Lite exportability to your long-term revenue model and international competitiveness?
Yeah, ITAR free is essentially what everyone outside of the US is aiming for. And that's just critical for the simple fact that the Canadian government requires it in order to provide funding. So that's ultimately, I think, where the value is that the US government can't tell the Canadian government what they can and can't launch, and when and where they can and can't launch their own sovereign product, because by definition, it would not be sovereign if it was ITAR.
For investors in this $4 million safe, What are the most significant risks that still remain at the end of this runway?
I mean, there are a ton of risks as it's a launch company. We'll have done a subscale hot fire test and we'll have built a great experienced engineering team. So it'll be de-risked in some ways, but in other ways, we'll still have some of the larger engineering challenges still ahead of us, namely the full scale hot fire, building turbo machinery, will be the other one. They call that like the great filter, the rest of the rocket and the subsystems and components. So we'll have de-risked in the sense that, we're going from almost idea and a light team and a piece of paper to, okay, we've got facilities, we've got a team in place, we've demonstrated our technical capabilities, but there will still be substantial milestones ahead that we'll have to continue to build for, but we'll be able to de-risk all of that by demonstrating our technical competence, which then releases another tranche of capital. By then, we'll also have received some sort of government grant or funding as well. So further kind of validation from the government. So we're de-risking some things, but trading that for risk down the line as well. But that's kind of the nature of most early stage companies.
And this question isn't in our question set today, but I think it's a vital follow-on question, which is, it appears that a significant amount of your time has been spent on partnership or relationship or co-opetition building as a component of de-risking. And would you see that as a vital strategy to dealing with the lack of vertical integration that exists within the Canadian ecosystem?
Yeah, absolutely. That's how we see it today. I mean, there's a reason why companies vertically integrate over time, and a lot of that is to control, costs and time and quality. To your point, I don't think the Canadian ecosystem has that capability, nor do I think being able to stand that up is a non-trivial challenge. So trying to go as quickly as possible while also leveraging what does exist within the Canadian ecosystem, like a flight termination system, makes a lot of sense because it can be a standalone system. It's designed that way for safety reasons, gives us the ability to offload some of that engineering and NRE and share that either with others, or allow someone else to develop that and then they can commercialize it and sell it. It's not secret sauce. Ultimately, the engine is, call it the secret sauce and one of the main differentiators. And I think trying to vertically integrate too soon, there are so many companies that see what SpaceX did, think that that's the recipe, and they try to bring everything in-house, and you just kind of trip over yourself because you're overcomplicating a problem just for the sake of, well, this other company did it, so therefore I should as well. So, Canada is also a very different ecosystem in place relative to the US and international. It's very nascent. So I think it's going to be a very iterative approach of where can we partner and how do we also de-risk that if the partner fails. That always has to be a question. You never go into a partnership assuming that, but you definitely have to, from like a risk mitigation perspective, and kind of take that approach. Otherwise, I think we're going to take the 10 to 20 year journey, substantially more capital, and it'll definitely be higher risk if we try to just bring everything in-house.
At the conclusion of this round's runway, what would failure look like, not just success, from an execution standpoint?
Yeah, so I'd say we expect failure, and we expect many failures, and that's really a function of treading uncharted territory. And we have a lot of experience on the team, which helps us kind of have foresight into what potentially could go wrong. But we do expect multiple failures, and it really kind of working through the test, fail, iterate cycle. And that's how you know that you're on the bleeding edge of the possible. And ultimately, that's a core focal area for us in the team.
How are you thinking about dilution management and ownership protection for early investors as capital requirements scale towards Series A and beyond?
Yeah, the main protector there's two. One is capital efficiency. So that's where bringing in experience helps. The other is non-dilutive financing from the government. And that's where spending as much time in Ottawa and wherever our stakeholders ultimately are will be critical to fulfilling that.
If the technical program goes well, but capital markets tighten materially, what levers remain under your direct control?
Yeah, it's a great question. The pace of development is ultimately, because it is a hardware rich development and cycle, we'd be able to alter the pace in a way that can also match budgets from that perspective as well. So I think that's probably the biggest lever in our control. I do think we are de-risked a little bit with the government having a lot of interest in this end market and opportunity, where they typically ebb and flow sometimes with capital markets as well. That's not directly in our control, so I will caveat with that. But ultimately, if you have to make tough decisions to ensure that the company sustains itself, I've done that historically at my last company, and we'll do it again. Absolutely.
Why is this moment uniquely important for Canada to build a domestic propulsion backbone? And why might this window close if execution is delayed? You've already mentioned a bit about this, the idea of sovereignty and globalization, but love to unpack that further.
Yeah, I think from a propulsion perspective, it's a very difficult problem to be solved. And it also, I like to call it the SpaceX effect or the PayPal mafia. If you can build Shopify is actually a great example of this as well. If you can build enough of a large enough of an ecosystem in and around a product or a company, it has spillover effects into the broader economy. And I think launch in Canada principally targets two areas. One is this spillover effect. I think it's like a 5-to-1 ratio of every dollar in creates $5 more into the broader economy within the launch ecosystem. And that's being shown in other countries. The other, actually, there's three. Another is you're attracting talent. It's a very engineering intensive problem to be solved. And you can attract very ambitious, technical, smart engineers to solve this problem. There's very few clean sheet rocket design opportunities globally. So this is a global opportunity. And then third, of course, is just the national defense and national security aspect of it as well. So I think across those three, you've got economic levers, you've got talent levers who then spin off and create their own companies in the broader economy. And then you've got national security as a third.
What would you say to an investor who believes launch is structurally too difficult, but agrees that propulsion IP is strategically valuable?
It's interesting because we started thinking, what's the quickest path to getting a rocket to orbit? And obviously the quickest path would be you buy an engine. But the interesting part about that is there aren't really engines to be purchased. And there's also, I think, a reason in and around that, in the sense that rockets are the development of a rocket is principally around the engine, that if you just bought an engine off the shelf, it's probably going to look and feel exactly like whatever rocket that engine is used in. And therefore you cede a lot of your competitive advantages and competitive edge. Launch also isn't like the launchers themselves. There aren't enough of them out there to warrant building your own engine and IP and then selling that. It's just not a large enough business. You see that with Ursa Major, and they've kind of transitioned to hypersonics and other opportunity sets. So I think propulsion as it relates to launch vehicles isn't a huge end market. And it also creates a structural disadvantage to whoever's purchasing the propulsion IP, because ultimately the competitive edge in launch is around launch economics. And if by virtue, one of the largest cost centers within a rocket, which is the propulsion system, if you're buying that from someone, they have to make a margin. So unless they, are able to manufacture a ton of them, which there isn't a large enough market for that to happen, and there's a lot of structural reasons why that wouldn't be the case. That's probably what I would refute on the propulsion and the IP side, unless, again, you're focusing on different end markets, hypersonics, missiles, etc., which those are also just very different propulsion types and technologies to begin with as well.
5 years from now, what must be true for CRC to be considered a success?
We will have launched a light lift rocket, like a Pathfinder. It'll be composed of one of our engines that we will then be upscaling at the rocket for medium lift. So that I would say that would be the ultimate sign of success. Short of that, I think ensuring that we've got a world-class caliber engineering team. I think indexing ourselves to the Canadian ecosystem would be selling ourselves short from a globalistic perspective. So that would be one element that I'm super hyper focused on. And that has to start from day one. And it does start from day one. So not diluting the strong team that we have currently. Engine hot fire. So we'll be one of the few companies globally with a Methalox turbo powered propulsion system in the world. That'll definitely happen within the 5-year time period. And then having a strong manufacturing and test facility that's being uplifted, built, as well as government grants, commercial contracts, and ideally a government contract as well for launch, just to demonstrate that we are and have been the team to continue backing.
What question do you wish investors asked more often at the pre-seed stage, and why?
Is this for like any company type, or is this company?
For this company.
Great question. It's a really good question. I feel like I'm gonna have to think about that one. Part of me leans towards a deeper dive on some of like the technical aspects, but it also shouldn't be an expectation, especially at the pre-seed. You're essentially betting on the founding team and the end market and their ability to execute. So maybe I've just been tainted both with my experience and expectations to just say, I think everyone's rightfully so focused on the team and our ability to execute that that's ultimately the most important question to be asked. And the one we get asked probably the most often, because there isn't necessarily any secret sauce that there's going to be a lot of IP that we'll be developing, but ultimately it's our ability to execute. So I guess long-winded way of saying I don't think haven't been asked something that I've been waiting, chomping at the bit for someone to ask something at the pre-seed stage, because it's so like team focused, I guess. Yeah, nothing really comes to mind.
Why is the approximately 5-ton to LEO class the right long-term economic and strategic segment versus starting smaller or going larger?
Great question. Yeah, so light lift has just been shown to be uneconomical. You're just not sending enough. You're not gaining enough revenue per flight to offset all of the operational and engineering overhead that's required to maintain and sustain. And with launch costs continue to be pressured downwards, it'll just make that class more and more economically unsustainable. On the large side, most of those rockets, and I guess I'll answer the middle piece at the same time. Medium lift, and what we're classifying as about 6,500 kilograms to orbit, you're really trying to optimize 100% of the utilization of that rocket as often as possible, because that's also a way of bringing your total cost down relative to, the Starships or the New Glens. And if you look at the average utilization of a Falcon 9 fairing, they use about 3,500 kilograms in total for their dedicated launch customers. And a lot of that is the sovereign type payloads or dedicated commercial constellation deployments to LEO and sometimes MEO. And I think that's kind of like the forgotten middle. And that's why we're really focused in and around that area, because there's a lot of mission sets that are focused in that, call it up to 5,000 to 6,000 kilograms to orbit. A lot of that's focused on the LEO economy, which is where most companies make their money. So it's also focusing in and around on that opportunity set. And then the larger rockets are more focused for the moon, the lunar economy, Mars, geo to a certain extent, space station deployments, large structure deployments, and ultimately those are massive government contracts that offset whatever loss. And that's why, Starship is hyper focused on full reusability, because they want to sunset Falcon 9, and they almost don't care if you put a couple thousand kilograms into a Starship, because the cost to launch it will, in theory, be really low. but they have to go through a lot of engineering hoops and hurdles to make that happen. Whereas if you size the rocket correctly and you don't get seduced by the large, I mean, we're in Canada, so we don't even have those large, billion-dollar plus contracts for these large like interstellar or interplanetary mission sets. It's just the perfect area for maximum payload utilization and fairing utilization, which gives us a really hard to beat competitive advantage because you can't just shrink your rocket down or increase its size. And that's where the market has been continuing to shift. And LEO will continue to be the moneymaker for the space economy for the next 10, 20, 30 years. And this feeds that perfectly. So that's kind of how we view rocket sizing and why we're focused on medium lift so heavily.
I usually like to end this interview with the following question. Why does space matter?
Such a great question. And in so many different ways. I think for me personally, it's just, growing up as a child, you always either A, look up into the stars or you're watching, movies, or I remember going to the IMAX cinema and it was, I think, like the Apollo mission. It was so cool and it's just so inspiring. And that ultimately is what led me to go into engineering. And I think inspiring, the younger generations to think bigger than, just social media apps and, B2B SaaS, which is the world that I lived in. We need a world of dreamers and we need a world of ambition. And I think space really solves that for a lot of people. And it really kind of helps, I think, progress society forward. So I think that's one element. The other that's more tangible and tactical is the global economy is so dependent on space infrastructure at this point that if you were to snap your fingers and all the satellites were to turn off, we wouldn't have financial transactions. We'd probably lose power. Our communication backbone would also falter. So a lot of what we depend on day to day is so heavily reliant on space infrastructure. And I think that's finally being understood post-war in Ukraine after, you had the GPS jamming and comms jamming. And I think militaries around the world were like, oh, this is a thing. So if you were to, as an adversary, disable all of the US's satellite infrastructure or like a cyber attack or something like that, you don't actually have to fire a missile or a gun in order to have a massive impact on your adversaries and their economies. Space matters so much more today than it did even, 10 to 20 years ago. And it's only going to accelerate as people talk about bringing data centers into space and power into space. So we're moving our key infrastructure off of Earth into space. And that just means how are we going to protect it? Who's going to protect it? And I think that's something that is not spoken about at all in media because you can't see it, you can't feel it, you can't touch it, and therefore you forget about it. But it's so integral to everything we do day to day that from a tangibility factor, it's probably one of the most important infrastructure elements for humanity.
Well, it's been a pleasure. Thank you so much for your time today. And we look forward to following up in a few months.
Absolutely. Thanks, Jason.
Thanks, Hugh.